So, good evening, everybody. This is Kazuya Yoshida speaking from Japan. So, tonight I will speak about the orbital manipulation things as one of the important topic of space robotics. Right. So that tonight, robotic systems for orbital manipulation. So, last week I spoke about planetary robotics, but tonight orbital robotics, and as I mentioned earlier, the two major applications of the robotics technology to the space development are divided in two application fields. One is a planetary exploration, lunar planetary exploration, and the other is robotic, mainly manipulation in an orbital environment. So tonight, I'll speak about my second topic, that is orbital robotics. So the orbital robotics, the major issue is to assist and expand astronauts' capability in orbital operations. For example, as a replacement or a complement of the human extravehicular activities. So for example, for the International Space Station, there are a lot of the activities by human astronauts inside and outside of the pressurized modules. So the human activities is great, but it takes a lot of cost and risk. So to reduce the cost and risks, the robotics technology would be very, very useful. And another application of the orbital robotics technology is a completely unmanned mission for the purpose of removable of dead or unnecessary or uncontrolled object from the orbit to prevent the increase of space debris. So you may know that today the space debris is becoming a problem as a contamination of orbital environment. So unexpected collision of the space debris with International Space Station, for example, or other functioning satellites cause a big disaster. So safety and security of orbital environment aspect, the removable of the space debris is very important. So, but this removable technology is very, very difficult. So at least we should not increase the number of the space debris. This would be a first priority. But anyway, for these two major applications, the robotics technology should be useful. So that this next slide is for the planetary robotics. This was a topic that gave you last week. So speaking about the orbital robotics, orbital manipulation technology and application. When I was graduate student of Tokyo Institute, that was early 1980s, I encountered with this very interesting picture. Actually, this picture was published in NASA report called ARAMIS, ARAMIS report, published in 1983. So in this NASA report, they discussed about the future of orbital robotic systems that could help us for the assembling tasks or maintenance tasks of the space structures. So this figure is quite obvious that how the space robotic system could work for the such a construction and maintenance kind of tasks. And this second one is very interesting. So in this picture, the a free floating satellite that has a multiple manipulator arms should work for the repair or maintenance of broken spaceship, for example. So by using this type of the completely unmanned spacecraft that has multiple robotic arms could be useful for the capture or retrieve of free floating object in orbital environment. And if the target is spacecraft, we can refuel, put fuel to the spaceship or spacecraft, or we can replace or repair some of the components, or we can reorbit, change the orbit to the safer place after the end of life. And also the assembling tasks are very essential. And at that time, 1980s, NASA seriously considered this type of space robot for the construction of space station. So, and this video clip is also very, very impressive. This was 1984. At that time, this was a space shuttle mission, and then human astronaut freely float in space. So he was making a spacewalk without any safety umbilical cord, and he was very brave. And he tried to capture a spinning spacecraft. So then finally, yes, at the moment of the contact, it had yes some impact and changed the dynamic motion of the spinning satellite. But finally, he managed to stop the spin and bring it back to the end of the manipulator arm. And then afterward, he fixed up this some problem in this spacecraft and give the spin again and put back into the orbit. So this type of the kind of rescue and repair mission was conducted by human astronaut. But so NASA tried this type of mission for several times, but they figured out that it's very, very dangerous, very risky, and very expensive. So afterward they didn't do any more such missions. But a very a reasonable consequence is that we should replace this type of the very dangerous, risky maneuver by robotic devices. So if we could develop the free-floating robot, we can replace such a risky tasks to the robotic operation. So the NASA conducted a lot of research in 80s and 90s, but because of the budget thing, they canceled the such a free-floating robot mission. Instead, Japanese Space Agency, at that time we called it NASDA, NASDA. NASA developed the free-floating robot, something like this, the spacecraft, unmanned satellite that has a manipulator arm on board, and conducted some challenging experiment. So this picture shows two spacecrafts, but at the launching configuration, that these two spacecrafts are connected. So then after the launch into orbit, then this small satellite was separated as a target object for this demonstration. So by using a manipulator arm, the Japanese Space Agency conducted some demonstration to make rendezvous and tracking the object by using manipulator arm, and finally capture and grasp. So the separation, rendezvous, docking, and manipulator berthing handling, this kind of operation was successfully conducted in 1997 and 99. So using these 3 years, Japan conducted such a challenging experiment. Then 10 years later, 2007, United States, not NASA, but DARPA, so Defense Research Institution conducted quite similar experiment named Orbital Express. And they also made a great success in a separation, rendezvous, manipulator berthing, capturing, and also the fuel transfer and assembling, and also the monitoring tasks by using a manipulator arm. So that we, mankind, have very basic technology and demonstration for such type of the orbital manipulation in future. But still, to make the space debris removable in practice, we need more and more technologies. For example, in many cases, the target has a spin or a tumbling motion, and the target object is no control. So all these previous demonstration, late 90s and early 2000s, the target object was controlled. The attitude was maintained, stabilized. So that this was a quite stable and quiet target. But looking at the practical cases, we need to deal with a more dynamic, uncontrolled target. So for the point of view of the control technology, tonight I can mention three major interests. So the first one is the control of the free-flying space robot. There's something like I showed you in the previous slides. So here the dynamics in control systems is very unique and interesting. And the second topic is a flexible manipulator control. And here the vibration dynamics is a major issue. And finally, I will speak about the contact or impact dynamics. So when we try to capture something in orbital environment, we need to deal with contact impact dynamics that if we make mistake, that this impact thing can cause a big disaster. So speaking about the free-floating manipulator control, we can find a very big difference between the ground-based manipulator and free-flying manipulator systems. So as you can imagine easily, for the space robot, free-floating space robot, the base body is free-floating. But for the ground-based manipulator arms, so industrial manipulators, industrial robot for production lines, the car assembly, and today we can find many robot manipulators in the factory. But all for the ground-based manipulators, we have fixed solid base. So this is a very big difference. So this is a quick review for the existing or conventional manipulator control for the ground-based robotic arms. So our concern is an endpoint. So usually at the end of the manipulator arm, we have a hand to grasp something, to assemble for these kind of tasks. We have a robotic hand at the end. So that our concern is how to control this endpoint with hand to get appropriate position and orientation. For this actuation, we usually have a rotational actuators at the wrist and elbow or shoulder parts. So usually these joints has a rotational motor. So the rotational joint angles and endpoint XYZ coordinate roll pitch orientation. So we need to the model for the relationship between endpoint coordinate and joint rotation angles. So usually this kinematics or geometry equation is relatively complicated using the sines and cosines of joint angles. But if we derive the equation in a first order differentiation, this means the velocity level. So joint angular velocity and endpoint velocity. In this level, we can get a relatively simple equation, something like this, by using the matrix here. And this matrix, if you are familiar with fundamental kinematics and dynamics of the manipulator, this is a very, very familiar matrix called Jacobian matrix. So this describes the mapping between a joint space and endpoint Cartesian space at the velocity level. So by using this equation, we usually control the manipulator endpoint, something like this. So we have the given command, the desired velocity for the endpoint. Then just by using the inversion of Jacobian matrix, we get a joint velocity. So from this configuration, if we would like to move the endpoint to the x direction with a given velocity, just put such a value, velocity value for the endpoint, then we can get the appropriate joint velocity to make it happen. So then we form this type of the feedback control to keep the track of the given trajectory or go to the given endpoint coordinate. So, but this this equation is relatively simple in case that the base point is fixed. However, in a space manipulator arm, in a free-floating base body, with a free-floating base body, we need to consider the motion of the base also. So actually the endpoint coordinate is described as a summation of the manipulator part. So that is represented by J times phi dot. But also the motion effect of the base body. In this equation, this is represented by JB times x dot b. The B is for the base body. So the Jacobian matrix for the base body, and here the velocity in XYZ and load PTO for the base body. So that we need to consider the endpoint and base body, two different things simultaneously. Usually the motion, three-dimensional rotational motion in an orbital environment is a very, very strange. So this is a real video taken in a space shuttle, and this is a scissor-like tool, and it shows a very, very strange rotational motion. So to us, it's very strange. But from the point of the natural or nature dynamics, it's quite normal. So we can relatively easily simulate the motion on such a cyclic spinning motion. So just that we are not really familiar with this type of the rotational motion in a microgravity environment. So because we are living in a gravity environment, usually we don't see this type of the continuous cyclic rotation. But everything can be understood by a very simple law, that this is the second law of the Newtonian mechanics. And so just applying the well-known principle of the momentum conservation. And just in case of the rotational motion, the things becomes relatively a little bit complicated and unfamiliar to us. So this slide shows the very basics of the Newton's equation of motion for a mass point in the left-hand side. So we know the mass and velocity and momentum. So momentum is just mass times velocity. We can define the momentum of the point mass. So then it's time derivative gives us a false. Oh, yes, false. So that I'm sorry that this dot is slightly shifted, but mv dot. So m times acceleration equals to force. This is a very well-known Newtonian Newton's equation. And for the rigid body system, we can find quite similar comparison and mass to the moment of inertia for a rigid body. So then angular velocity and angular momentum is defined just I times omega. So then take a time derivative, we can get the such an equation. And so time derivative of angular momentum is equals to the moment. So then this moment, just to expand this equation, we get this type of equation that is usually called Euler's equation. So that for such strange looking spinning motion in a previous video clip, but this motion can be understood by this simple Euler's equation. So just going back to the robotic manipulator things. The robotic manipulator is a bit more complicated because there are multiple rigid body, and the multiple rigid bodies are connected by a rotational joint. So, but as a result, we can get simple equation for the momentum conservation. So the second equation is an equation for the momentum conservation that is composed by inertia, moment of inertia term, and velocity term. So that this xb dot is a velocity component for this base body, and HBM is an inertial term for the manipulator component, and a phi dot is manipulator joint velocities. So just keep the same fashion, the inertia times velocity, that makes the momentum of this entire system. So this is the governing equation for the space robotics system, multi-body system in free floating environment. And as far as there is no external force or moment, that this quantity will be maintained. So then, knowing this fact, that we can solve this first equation for the manipulator control. Just I had when I was a graduate student, I had this idea to solve the second equation for xb dot, then put into the first equation. We can get very simplified equation. But anyway, this is the definition of these symbols. So that again, this is the first equation for the velocity relationship for the robot hand control. And a second equation is a momentum conservation. Then solve the second one for HB dot. HB dot is a base motion, but in this case, base motion is not important. It's not our primary concern. So then eliminate this term by putting into the first equation. Then we get such an equation just by using xh dot and phi dot. And this is the term that including L, angular momentum, is a kind of offset. And in case of the zero momentum at the beginning, this term becomes zero. So then we get very direct relationship between phi dot and xh dot, even though that we experience some reactive motion onto the base. So the base moves due to the reaction, but in this equation, we don't need to concern about it. Just looking at the endpoint and joint, then we get a smart relationship. So just in between, we get this term. This term is composed by a manipulator Jacobian plus, actually minus, some additional term. So what is this additional term? The additional term includes HB inverse and HBM. So HB is an inertial term for the base body, and HBM is an inertial term for, actually coupling inertial term for the manipulator arm. So this tells about the relationship of the inertia between the base and the manipulator. So anyway, so this equation describes the relationship of the manipulator for the manipulator endpoint. And so I had this idea in 1987, and then I spoke with my thesis advisor, and he gave me a very special name for this matrix. This is a kind of the augmented Jacobian matrix, but he likes, and we like to use generalized Jacobian. And why this is generalized? So that we discussed, the primarily discussed this type of the system, the satellite that has a manipulator arm. But this equation that I obtained includes all different cases. So in one extreme end is manipulator arm system mounted on very, very massive base body, which is the Earth. So in this case, this base body inertia term becomes almost infinity. So in this case, this additional term becomes 0. So then we get the conventional Jacobian matrix for this type of system. So then in this case, this base body inertia is not so big comparing to the manipulator arm. So this second term cannot be negligible. That's why we have the reaction effect from the manipulator arm. So then for the other extreme end, when we have a very, very small base body. So in this case, the system looks something like this. So that it's a kind of the free-floating snake in the orbital environment. So for this case also, we can apply this equation by putting appropriate values for all these inertial terms. So then we made a fundamental experiment to confirm this idea. Actually, that was late 80s or early 90s. We didn't have high sensitivity cameras. Today, the motion tracking system, we can get a very sophisticated system very easily. But we tried a lot of effort. And first of all, anyway, we wanted to simulate the microgravity environment in the laboratory, ground-based laboratory. This was a very difficult question, but we prepared a flat table and air tank, pressurized air tank. Then by using the pressurized air, that actually this robotic system is slightly floating on the flat table. So we can demonstrate the motion of the zero gravity. Actually, in this case, the frictionless environment onto the for the two-dimensional motion, horizontal motion. So we put the target marks by LED and also the fixed target point. Then in this case, the manipulator arm moves from the initial point to this target point. Even though during this operation, the manipulator base body rotates to the different direction because of the reaction generated by this manipulator motion. So this is the snapshot of the motion profile. So I gave the command from the initial point to the target, the endpoint should travel on a straight line. And in this case, this is the center of gravity, and it's slightly shifted because of the small friction, but the center of gravity, its position is maintained because of there is no external forces or moment. So the entire moment of this system is conserved. So then the reactive motion occurred on the base body, but still the manipulator endpoint control was conducted in an appropriate way. So when a Japanese demonstration satellite, it was named ETS-VII, Engineering Test Satellite number 7, for the demonstration of the rendezvous docking and space robotics operation in an orbital environment. We had a very good opportunity to test our control theory to verify that our idea of the manipulator endpoint control in a freely floating environment. So, by the way, that this was a Japanese national mission. So, the many Japanese research institutions conducted a number of the different experiments, including such a manipulator motion and the peg-in-hole tasks, assembling components, deploy retrieval structures. But much more interesting thing is dynamics and control and capture and pathing. So for this purpose, my theory was very useful because that we are very much interested in the manipulator endpoint control in a three-dimensional inertial space. So by the way, that this video clips shows the real operation of this Japanese robotic spacecraft. And so this was a Tsukuba Space Center. And so the front row was the specialist to control the manipulator arms. And on the second row, as an observer, I'm sitting, and my students were looking at this experiment. And this left top corner, we have onboard video images from the spacecraft. So currently, the manipulator arms was moving from one place to another. So that's why from the manipulator mounted camera, we see the motion of the manipulator arm. And so, for example, we were very much interested in this type of thing. This type of control. So having completely freely floating target nearby this spacecraft, and by using manipulator arm and try to track the motion and capture safely. But this was the space agency considered this was very, very dangerous. So so they didn't give us a real floating target. So just for just experimental purpose, we assume the virtual target, then try to move the manipulator arm to follow the given trajectory in inertial space. Then we check the motion track of the endpoint. So actually, this was the pitch inertial pitch motion of the manipulator arm. As you see, that this is 22.8, 0.6, 0.0. So with a very small error, just plus minus 0.1 degrees, this manipulator endpoint follow the given track, even though the even though the base body had a significant amount of the reaction. So this tells the amount of the reaction. This was not really big, but something like within the plus minus 1 degrees. But with this endpoint control, the target error was very, very small, the plus minus 0.1 degrees. And this is another experimental result we conducted in an orbital environment. So it's just a very simple, looking like a simple manipulator control. But this is a time history from here to there, 0.8, the endpoint velocity, and that this is the amount of the momentum, the reaction due to this manipulator motion. So in this case, usually if we move the manipulator arm from a point to another, this action causes the reaction just by the spacecraft has a disturbance on the attitude. But because of the reaction wheels, this disturbance can be absorbed after some while. But this is the time, so it takes some 100 seconds or several, almost 100 seconds it takes a few minutes to recover the orientation. But we figured out a very special trajectory that looks like a straight line, B to C. That just this is the endpoint velocity. So with almost the same velocity, move the point B to C. But this is a very special trajectory. In this trajectory, we don't get any reaction back to the base. So that's why we don't see any disturbance on the base body. So we, as a result of the discussion I made using these equations as I showed you previously, we found another characteristics for the special trajectory that will generate no reaction back to the base body. So I will give you another example for the same dynamics in the second topic.